Hey everyone, in this tutorial we'll learn how a goal-oriented action planning AI system works on a technical level, and we'll learn how to implement and extend it in Unity and C#. A few disclaimers. First, I've adapted code for the framework of the AI system and a couple of other features, but at the time of this recording, everything is under an open source license, and all artwork is either open source or it is my own poorly drawn creation that you can all feel free to use. And everything is in the description if you want to know more. Second, this code is imperfect, and imperfect code is great for generating discussion. So if you see something you could improve on in the code, leave a comment here or on the subreddit to help people out, or even better, fork this, add to it, and contribute to this month's AI game challenge. Once again, everything's in the description if you'd like to know more. Alright, let's talk about the GOAP AI system. First, this is an article by Brent Owens, who wrote the code that we'll be basing our AI system's code off of. So we're going to make a combat-oriented action game today using the exact same base as this is using. So the example he uses throughout the article, which you should read to get some context and background knowledge, I highly recommend it, but the example he gave is this resource gathering kind of system where it looks like we have miners and woodcutters, and I believe they have to get tools and the tools can break, and let's say you want to get wood, you could either collect twigs or you could chop down the tree, but you need a tool to chop down the tree. There's costs and benefits. You can see how it would be appropriate for the GOAP AI, the planning system. And this shows how whether we make a combat game or this sort of game or this sort of system, the framework can apply to any genre, any gameplay style, but there are different frameworks suited for different types of tasks. So that's what you as the architect or software engineer have to decide, is which costs and benefits of different frameworks make sense for your specific project. Now let's take a look at what I came up with. It's basically Zelda, but much worse. And we have a shield, so while we hold up the shield, we take half damage. While we swing our sword, we do damage. And then we have our hearts in the corner. And so we're going to go over here and aggro this wolf, and he's going to chomp at us and take a heart out. And while he's regaining stamina, he's going to chase us around. So you'll see we took half a heart there because we had the shield up. So he's just going to chase us around and try to eat us till we die or he dies. So the wolf, we'll look at him as an example. He is probably the most basic enemy we could make under this gameplay system. So our gameplay is just we can move around, we can shield, we can attack things. That's it for right now. And the wolf, other than the move to and idle states, his only other action is to attack. So he has just this attack action, and it's attached as a component. We'll go through all this later, but that is a GOAP action. So we have to attach each extra action that we want as a GOAP action. So whether that's cast spell, dash attack, everything special we want our character to do will be a component. Everything that we want the planner to consider as an available action. And then you'll notice he has this GOAP agent script attached as a component. And this is indicating that he is a planning agent, meaning he is an AI that is going to do actions. And we'll go through this later because this is where everything comes together. This is the interface for the planner, for the finite state machine, for the whole system is coming through here. And then completely separately, this was written by me. This is my gameplay logic for the wolf enemy, and this inherits from an abstract generic enemy class. This has everything in common to all enemies, and then we have the wolf, which inherits from that has things specific to the wolf, like for example, its speed or stamina will be different from other enemies. And so that's the basis of what it looks like when you make a new enemy. You attach the GOAP agent component, you attach all the actions you want, and then you add any additional logic you want for your specific gameplay. So right now we're just going to look at the planning logic. We're going to ignore the gameplay stuff for right now. So let's take a look at this GOAP agent class that was attached to the wolf. So you'll see we have a reference to a finite state machine over here. We have references to its available actions, its current actions, and then we have this data provider, which is iGOAP. So this is a GOAP interface. And then we have a GOAP planner over here. So it has references to everything but the actions, which are attached as components to our object. So this is where everything kind of comes together. So I'm going to give just a general overview of what's happening and how things fit together. It will by no means be comprehensive, so definitely look up the article, or just download it and set breakpoints and see for yourself how things work. That is really the best way to do it, and I cannot simulate that through a video. So the GOAP agent, this is the wolf or the miner or whatever is doing things. So you'll notice here at the start, we're initializing pretty much everything, and what's most interesting here to me is these create states. You'll see that we have references to states of a finite state machine up here. And what we're doing is creating states dynamically. So as soon as the world loads, as soon as we need to construct a new plan, a new finite state machine, we're going to, for example, create a new idle state. So first, we get the world state. And what is the world state? It's basically describing the environment around us, the information available that we need to adjust our plan around. So for example, in the resource gathering, we need to know where the wood is, where axes are, where everything is, if it's available or not. And we're going to define this with a key value pair. So for example, our world state might say axe available as a string, and then we have a bool that's set to true or false, so that when we look up is axe available, we can look that up as a key, axe available, and then we'll see the bool true or false if it is or not. So that's how we're going to describe our world to our agents. And then we have goals. So we'll look really quickly. The wolf over here, the wolf and all enemies inherit from GOAP. So all enemies inherit from GOAP, meaning that they all need to have this create goal state function. And this is describing what we want our AI to do. What is their goal? Is it to gather resources? In this case, it's to damage the player and to stay alive. So there's two goals going on here. And in more modern games, you might have a lot of different goals. You might even have trees of goals describing the priorities, which ones you should abandon, which ones you should continue to pursue. But for now, we're just going to say stay alive and damage players. So defend and evade and then attack. That's what we want to have happen here. So going back to GOAP agent, it's going to create a goal state based on our enemy, so the wolf, and it's going to describe the world to us. And so we need these things to construct the plan. So we're going to call this plan function from the planner, which is a big fat thing, building a graph, and then spitting out a queue of the exact sequence of actions we need to take to reach our goal. So in the wolf's case, the action wolf attack, its effect is damage player. So you can see the wolf's goal is damage player, the attack action's effect is damage player. So that's a very simple plan. It just needs to do that action as much as possible while it still has stamina, while it's in range. It needs to just attack over and over. So this is probably one of the simplest enemies we could design. So there's this huge thing, finding a graph, we get a queue spit back, and so if we have a valid plan, we're going to set our current actions all the way up here to be what we just found in that graph, what path, what sequence of actions we need to do. And then we're going to report back to our data provider that we found a plan and it's successful, because we might want to handle things differently if our plan is unsuccessful. We might want to find the next shortest path. So when we load up our game for the first time, we're initializing, we're making the wolf, we create this idle state, and so that's what we're doing dynamically. We're setting this variable up here, this state, which is initially blank, to create this plan and to populate the finite state machine. So then when we push the idle state again, let's say our plan failed, we push this idle state again, we perform the idle state, and we try to construct a new plan as much as possible and readjust based on the environment. And then here we have the move to state. So we had three states up there, idle, move to, and then a perform action state. So in this case, the move to state is handling whether or not an action requires the player or the target to be in range. So in our case, we want the player to be in range. In the resource gathering case, perhaps the target are the resources. So in this case, if our action requires that something's in range, but we have no particular target, like the player's not in range, the player's off the screen, then we're just going to remain idle. But otherwise, if we can move the agent, in our case, this move agent function is going to be coming from our abstract enemy class. When you see data provider, in the combat case, it's from the enemy class. In the resource gathering case, it's going to be from the workers. We're going to call this move agent, and that's going to return a bool whether or not that move was successful, whether it was in range of the player that it could chase, because if you have the player outside of the enemy's radius, it's not going to move, it's going to return false. But if you've defined an aggro radius and the player's moved in that, then you can set move agent to true and you can move the enemy forward. And so then we're going to pop this move to state, and then it's going to check in the plan if we need to do another move to state if the player keeps going out of range. Now this last one, perform action state, first we check if we have an action plan. If we don't, then we're going to go back to the idle state so that we can create a new one. And then we're going to look at our current actions, because that will be what this state is going to become. So whether it's our attack action, cast spell action, we're going to take that off the queue because we're trying to perform it right now. And first, we check if we need the player to be in range, because like I said in the other video, the in range and move to is a special condition that's very common to almost all actions. It's something that's very commonly needed. So we're not going to handle that in our preconditions and effects. We're going to handle it over here, because if the player is in range, then go through and try to perform it. If you can't perform the action for whatever reason and it fails, go back to the idle state, find a new plan. Otherwise, we're going to keep pushing the move to state until we're in range. One thing you might be interested in is this interesting syntax over here, so I'll explain it briefly. So when we have these create idle state, create move to state, you'll see that it has this variable that we had up at the top, and it's equal to this kind of functional programming looking syntax. And so let's look at first what the FSM state actually holds. So it's an interface that holds a function. It's just an update function that's overridden with some parameters in it. And then the finite state machine itself is just a stack with these FSM states. So it's a pretty typical structure. You can pop a state, you can push a state, and then on update, we're going to peek what's at the top of our stack, what state, whether it's a move to or an action, and then we're going to invoke its update function dynamically. So just to summarize, we start up, our wolf's being initialized, we create all of these new objects, we create the update functions dynamically for these different finite state machine states, and then we start in the idle state, which creates a plan for us, and then based on that plan we'll either push an action state, and then that might push move to states or idle states, and we just keep making up new plans as different plans succeed and fail and as the world changes. So that's what's basically happening here as the flow. But now let's take a look at the planner. So this is what's constructing the graph, and this is really the last thing that I want to touch on just to show the overall framework. So here's this plan function that's being called over here. So let's take a look. Yes, so in the idle state, we have the planner.plan function being called, and this is where it takes our available actions, our world state, and our goal of our object. And what it does is first, it looks through all the actions and it clears them. So if we had any Boolean variables, clear them because this is a new action. And then we're going to look at what's usable. So this is a good time to look at our wolf's attack action. See this check procedural precondition? So we have our wolf attack action, for example. This is a very simple one. And there's no precondition to it, just the effect is that it damages player. Damage player is true. And it has a stamina cost of 100 for now. So you see when we reset, we're going to reset our target. We're going to say it hasn't attacked yet. And then let's go down here, check procedural precondition. In this case, it just means that we need to have the player as a valid target, and that's it. So this will return true because the player is valid, and then this will say, okay, attack is a valid usable action. So usable actions will have that added to it. Now let me briefly show you another enemy with a little bit more complicated action. So this is Abigail. That's the name I chose for this kind of shield knight whose concept is yet undeveloped. But she has an attack and then she has this move, or it's really a dash attack. I should change that name. And so these are her two actions. So she can attack or she can do this dash, which is an evasive maneuver to dart away, hopefully avoid your attacks, make it harder to get her. Allow me to show you what Abigail does. So we're going to trigger her and she's going to dash around because we're not blocking, so she doesn't view us as open. See, we're attacking. She's trying to avoid our attacks. And now we're blocking. So she is going to try to cast a spell. So I know that doesn't look like what I had imagined in my head. I imagined that she'd like have a shield over her head and then fireballs would go down, but then I I got impatient with like drawing the fireballs and stuff. So this is what we get now. We get a half cast spell. And then we're going to try attacking again. She's like, ah, no, we got to get out of the way. So that's basically what she does. It's a very binary system, and I'm sure you all could do many more clever things with it. Because the wolf, he's very stupid. He just runs after the player no matter what. There isn't even a check to see if he has enough stamina in this procedural precondition. We don't even check if he has enough stamina. He'll just keep running and chasing after you. He'll regen stamina while he's chasing after you, but that leaves him open to a lot of hits. So he's just blindly running after you, trying to get at you. Whereas Abigail, she's going to be a little bit smarter. We want a duel with a knight to feel a little bit more intelligent. I'm using intelligent in air quotes right now because this is pretty basic. But she is going to check if she has enough stamina before even considering this as an attack to put in the planner. And then she's also going to look, is the player defending or attacking? So in this case, she's only going to attack when the player's defending because she knows she's safe if the player's sword is not drawn. And so you see this attack action fulfills the goal of damaging the player. Now this dash action is meant to be an evasive or defensive maneuver. So she's only going to do it when the player's attacking to get out of the way. And this fulfills the second goal of all enemies, which is to stay alive. Now, you also notice with this attack action, it has a cost of 300 and this dash has a cost of 400. In this case, we're going to view cost as least benefit. So in this case, a dash, it is preferable if she can do it whenever she can because it's going to keep her harder to hit. But the attack is really better because it's going to do damage. Right now, the damage system isn't implemented. We're going to view this cost as a lower cost means more benefit. So the way we calculate the stamina in this case, and I apologize for this magic number right here, you can see I have a little to-do marker here, but we're going to subtract from this magic number of 500, or really any scaling factor that you want, we're going to subtract the cost from it. So in this case, our cost is 300, 500 minus 300 is 200. So we need our stamina to at least be 200, and that's how much we're going to deduct from her stamina is 200 for the attack. Whereas for this dash, 500 minus 400 is 100. So the dash has less stamina cost because it's less beneficial. So this is where it can get a little confusing. So we have our cost of our GOAP action, which is going into our graph, and it's saying this action is more costly because it's not as good. The dash is not as good as the attack. We'd prefer to attack. So we're going to make the attack less costly or more beneficial. But then down here we have this scaling factor. We subtract our graph cost by this scaling from the scaling factor, and we're going to say that's how much stamina this costs. So the more stamina it costs, the more beneficial it is. And so that's kind of just our basic linear relationship. Hopefully that makes sense. But you'll see the procedural preconditions for this are a little bit more complicated than the wolf. So we're checking if our target is not null, but then we're also making sure that the player's blocking. So the player has this variable that's set when the animation is fired, the animation for blocking or attacking. It'll switch is blocking on and off. So we want to make sure the player is blocking. In this case, this is the attack action. So we want to make sure the player is blocking. If it's not, this will not go into our list of available actions in our planner. It will stop right here. And then we check if we have enough stamina, because if we don't, we're not going to want to run in and attack if we don't have enough stamina. We're not going to want to chase the player around if we have nothing in particular we want to do, unlike our silly wolf friend. Now let's go back to the planner, and let's say we're using Abigail as an example now. And let's say she's only able to dash because the player is attacking. So her only available action right now is to dash. And so we go through that, and this is a recursive function. If you see down here, this function is called build graph. We're going to be calling build graph recursively to generate the different branches of nodes. So here we're going to check if the parent node has the effects that will satisfy our preconditions. So for example, we don't really have many preconditions here, but let's say we added a precondition called can act. Like let's say there's a stun spell, and so there's a variable of whether or not you're stunned, whether or not you can even take an action. So that could be a precondition. And we might have an action with an effect that allows you to act. Like let's say anti-stun potion has the effect of can act. And so then the way we would chain it is if she's stunned, then we'd use the anti-stun potion. It has effect of can act. And then now we can finally chain to our dash action, which is what we wanted. So that's what this planner is going to construct recursively. And then besides just making a valid graph, besides making valid paths of nodes, we also want to keep track of the running costs. So if you remember, the dash action had more costs than the attack action because we'd really prefer to do the dash action if possible. In this case, we kind of have a binary decision because we're just basing it very black and white off of is the player attacking or not. But, you know, if it gets more complicated, we need to know the running costs as we build this graph. So when we exit out of build graph over here, let's say we are successful, we're going to find the cheapest leaf. So a leaf is the starting point, one that has no preconditions. In this case, I think all of our actions can qualify as leaves, but we're going to go through, and then this is where we construct our queue. We find our leaf, we go through the path of the graph, and then we on-queue or push every action to our queue along that path, and then we're going to return that in our GOAP agent, which we discussed before from our idle state, and we'll use our finite state machine to construct what states we need and how we need to update our enemy based on what states are supposed to come up next. So that's the bulk of what's going on here, but I'll briefly show you the logic for my enemies. So this is my enemy class that inherits from mono behavior and iGOAP, and most of the stuff I'm sure you guys could figure out, but the main thing to look at is this min distance and aggro distance. So down here, this is the move agent function that's a part of iGOAP. So this is what we use in our move to state. This is the actual logic behind how we're going to move our enemies around. And so for everyone right now, we can override this in the wolf class, for example. If we want the wolf to have a weird zigzag pattern for whatever reason, we could override this and make a different move agent function. But for right now, we have an aggro distance that will trigger the enemy to chase after the player, and then we have this minimum distance, which will allow us to say, okay, you're allowed to perform the action now. You don't need to keep chasing. So those are the two things to keep in mind over here. Otherwise, the enemy's main differences are in their stats. So for example, Abigail has a bit more health. She has a faster regen rate than the wolf over here. You can see he has a regen rate of 0.5. She had one of 3. He has a max stamina of 100, so on and so forth. This is where you just get to adjust the stats of your characters, and we could add and subtract different goals beyond what the basic enemy class had. And I think this is redundant and I might need to delete this, and I'm finding this out now while I'm filming. This has happened multiple times. I've found lots of weird mistakes. Alright, well that's about it for me, but I hope you guys found this tutorial helpful, and I hope you consider making some stuff of your own or adding on to this for the Game Dev Challenge. And feel free to leave comments or questions below or in the subreddit, and subscribe if you want more tech and game dev content. But most importantly, have a happy day wherever you are. I'll see you guys soon. Bye!